What's a vector? So in the basic sense, a vector is a quantity with a magnitude and direction. But what does that mean? Well, I'll give you an example from the real world. Speed and velocity. So speed is not a vector. Speed is just always a positive number that gives you a sense of how fast you're going, regardless of what direction you might be going in. So speed is what's called a magnitude. Now velocity is a vector because it has both an amount and then also a direction. Now in the one-dimensional case, the magnitude, so say you're going 4 miles an hour, but you're going backwards. So you'd be going, say, -4 miles per hour. So the magnitude would be 4, and then the direction is indicated by the sign. Positive for going forward and negative for going backwards. That's just in the one-dimensional case. Okay. And then in the two-dimensional case, obviously you could be going at a certain speed, but then in any direction, which way you like, in the plane. Okay. Now, in the discussion of vectors, there are going to be definitions or examples, and typically it will start by being given in 2 dimensions. But sometimes I'll start with an example in 3 dimensions. All the ideas that we're going to discuss, or most of the ideas that we're going to discuss, any number of dimensions is possible. We already saw this for the distance formula, that we can extend from 2 dimensions into 3 dimensions. Same thing is going to be true when we talk about vectors. And in most cases, the definition is going to be an obvious natural thing, just like it was with extending the distance formula. Now, there are some rare cases where an idea that we give does not extend to a different number of dimensions. And that's like important, and I'll mention that specifically. Okay. So now let's talk about vectors. A vector is determined by starting point and ending point. Or that's one way to determine it. So what's the notation for a vector? Well, if you want to emphasize the fact that you've got a start point and an end point, you want to emphasize those 2 points, you can write a vector like this. From point A to point B with a little arrow.
Doesn't that represent a ray? The arrow represents.
On the other hand, if you want to emphasize the vector as just one object that has a magnitude and direction, you can just write it like this. Just one letter like V. Mathematicians use V. Guess why? V for vector. A little arrow on top. So now there are a couple different notations. Sometimes there's the full arrow. Sometimes there's like the half arrow. And sometimes you'll see just a bold letter. Now bold letters became particularly popular in the older books, where it was harder because of the limitations on the printing to put an arrow over a letter. So they just used bold letters. Yeah. So because of that, it's actually relatively common for that reason. Personally, I like using the one with the arrow. Where possible, I like using it with the arrow because it reminds you that it's a vector in a very visual way. But the bold notation also means it's an arrow. Oh, excuse me, also means it's a vector. Okay. So suppose you have something that starts at the point 47 and goes to the point 53. What is that vector? Well, first, let's draw a little picture to see what this means. So what this means is we're at the point 4, 7, and we're going to go to the point 5, 3. And remember, vectors have a magnitude, which is this, but also they have a direction. So which is the start and which is the end is important. So it goes from here to here, so it's going in that direction. And so that's, yes, and so that's how you can represent a vector. Now when we draw vectors like this, we draw that arrowhead in order to represent the direction it's going in. But notice that with vectors, it's understood the line does not continue forever. That just indicates the direction, not the fact that it goes on forever. That's very important because vectors do have a certain magnitude. Okay. So that's the picture of that vector. Now, what is the vector itself? Well, so it goes from 4 to 5. So the x-coordinate goes from 4 to 5. So the x-coordinate is increasing 1. So that's your vector. So you get that by saying 5 minus 4. And then what about the y-coordinate? The y-coordinate is going from 7 to 3. So that's negative 4. So your vector is 1 comma negative 4. And if you look at the picture of the vector, it should make sense that 1 comma negative 4 describes that vector. So now, so the vector from one point to another point is like this, x2 comma x2 minus x1 comma y2 minus y1. Now, notice that the end calculation is just 1 comma negative 4. So that kind of looks like a point. But you can also see that in a sense it represents the vector that we drew. So if a vector is given by one point, we think of the starting point as the origin. So in other words, this vector is equivalent to this vector. I drew that more or less right. Okay.
They're parallel, right? Isn't it parallel?
They're not just parallel. It's the same vector. I just drew it starting somewhere else.
Oh, all right.
So in a sense, a vector is defined to be the same vector regardless of where it starts. Okay, so the vector 1 comma negative 4, those are both the vector 1 comma negative 4. It's just one starts at the origin and the other one starts at a different point, 4 comma 7. Both of those represent the vector 1 comma negative 4. Does that make sense? Okay. Okay. And so this was a question, I think. So one option to describe a vector is to state the magnitude, then give the direction as an angle. So for example, you could say the magnitude is 5 and it's pointing up, so the angle would be pi over 2. Those are polar coordinates. Or the equivalent in higher dimensions. So in that case, you're using polar coordinates instead of x, y, z coordinates. So you could choose either one. Right now, we're choosing to use x, y, z coordinates to describe a vector. So for example, we just said the vector is 1 comma negative 4. So we haven't actually said what the magnitude is, but we can figure out what the magnitude is, and we're going to do that very shortly. So first, scalar multiplication of vectors. What does that mean? You can multiply a vector by a constant. So for example, if you have the vector 1 comma 2, it roughly looks like this. So we can do a couple different things. If you multiply it by 3, it becomes the obvious thing. 1 comma 2 times 3, or the vector 1 comma 2, if you multiply it by the number 3, it just becomes 3 comma 6. And notice that the vector then looks like that. Okay? You can multiply it by half, or 0.5. And then the vector 1 comma 2 becomes the vector 0.5 comma 1. And visually it looks like that. You can also multiply it by negative 2. So if you multiply by negative 2, it becomes negative 2 comma negative 4. And the vector now looks like that. Now, in particular, notice that the magnitude has doubled, but it has flipped in direction because of the negative. So that's one of the cases where it's useful to have that arrowhead to let you know what the direction is. And then this works in the natural way for vectors in 3 dimensions, or any dimension. So in general, if you multiply a vector by some number, then the way that you find your new vector is you simply multiply each value, or each component, by your constant. Okay. So for example, for vector -1, 4, 2, if you multiply that vector times the number 3, you get that. -3, 12, 6. And once again, however long it is in space, it simply triples. But it's still heading in the same direction. So that's important to note, that when you multiply a vector by a constant, it's still in the same direction. It's just longer or shorter. In the same direction, it might be headed forwards or backwards, but it's still on the same line in a sense. The next nice thing we can do with vectors is addition and subtraction. So in general, and also for this topic, it can be helpful to think of a vector as a change or a displacement. Like we did when we defined a vector, we said a vector is like going from point A to point B. That idea. So imagine making a trip starting at point A and then taking the move indicated by the vector u to point B. Here I've got a little picture. Then, once you've arrived at B, making the move indicated by the next vector v, and then headed to point C. Now notice this. Each part of your trip is a vector. So the u is a vector and the v is a vector. But also you could think of the entire trip in one step as a vector. And if you draw it on the picture, I've labeled that w. So this gives us the idea of vector addition. So if we first do the trip u and then do the trip v, that's just like doing the trip w. Only now instead of saying trip, I'm going to say vector. So u plus v equals w, and the way to get that is to add the vectors value by value, or in other words, component by component. So for example, what if we have these two vectors and we add them together? So what does that give? Right. So you add these two vectors together and you get the vector 4, 2. Okay, so what does this mean geometrically?
Wait. I think, I'm sorry to interrupt, Professor, but this is to be u1 plus u2.
So the picture, okay. So we've got 3, -2. So let's see. So first we go 3, -2. So remember, when we don't have a starting point, we assume the starting point is the origin. So we go from here to here. And then we go 1, 4. So you go 1, 4, like that. So in a sense, this is your u and that's your v. But then we want the whole trip, and the whole trip was this one. So we just calculated that the whole trip is 4, 2. And looking at the picture, that should make sense. So again, you can also do this in 3 dimensions. So in 3 dimensions, you do the natural thing. You add the x components, then you add the y components, and then you add the z components. Okay. So let's add these two vectors. So what do we get? Okay. There you go. Now, naturally, trying to draw the picture for this becomes quite hard because it's hard to draw 3-dimensional objects, particularly vectors, because the direction becomes flattened out on a sheet of paper, so it gets kind of hard to register. So I'm going to skip drawing the picture for this one, but it's nice to have the two-dimensional picture, which gives us the idea of what's going on. Okay. Now, you might say that why did I draw, in the previous example, why did I draw the vector v starting at a different point? Shouldn't it start at the origin, because that's what the vector is? Well, we can use a parallelogram to look at this full picture. So first, let's look at the first parallelogram, because that represents addition. So the dot in the corner, think of that as representing the origin. So in that case, you've got the vector u and the vector v. So how do you add them together? Well, you can go, first you can follow the u, and then how do you add on the vector v? Well, a nice way to see that is through this parallelogram, because since it's a parallelogram, this vector v and this vector v clearly are the same thing. So you can just follow u and then follow this sort of parallelogram v. And that gets you to this ending point, and we can say that that's u plus v. So again, the v on the left and the v on the right represent the same vector because they have the same magnitude and they have the same direction relative to their starting point. Now, all that being said, this picture shows something else that's really nice, because there are two ways to get to that ending point. In this case, we did u and then v. The other way is to start by going this way and then this way. Algebraically, that would represent v, first doing v and then doing u, so v plus u. So this parallelogram actually represents a visual proof that u plus v is the same as v plus u in terms of vectors. And you can also prove it algebraically using the definition of vector addition. And what about the second parallelogram? The second so algebraically, one vector minus another vector is exactly what you'd expect. You do the x component, the first x component minus the second x component, et cetera, et cetera. So that's very straightforward. But visually, what does it look like? So imagine we're trying to say what u minus v is. So I've drawn u and v, again starting at the origin. But then what I've done is I fill in this other side. So if we think about it, we can see that side is actually u minus v. So there's a couple ways to think about that. Number one, we know that if this vector is v, then we know that the parallelogram vector on the other side, but going in the opposite direction, is negative v. So simply tracing out u and then negative v gives you u minus v. That's one way to see it. Another way to see it is to simply draw u and v and then connect them and then fill in the blank by vector addition, because you have v plus something equals u. Well, v plus what gives you u? V plus what gives you u? This has to be u minus v. And that's what would give you u. And once again, this parallelogram side and this parallelogram side are the same. They have the same magnitude and the same direction. Now that we've talked a little bit about vectors, I just want to mention a couple of different notations that we use in order to represent vectors. Okay, so one thing. First of all, vectors can be written as columns. So far we've written it as like x comma y comma z, the way we traditionally write a point. This is another notation for vectors, writing it as a column. Now, this notation is useful. In fact, I like it a lot because say you have two different vectors next to each other, you can compare their components directly. So for example, if you were to write down addition, writing down addition using column vectors is really nice because you can just read across. Instead of having to search for the x component in the first one and search for it in the second one, in this, as a column vector, you can just add straight across. So visually, it's really nice. But once again, in old textbooks, they didn't have the ability to stack things, so they didn't use, it was impossible for them to use this notation. But in modern books, you'll often see this notation because it's much nicer. Okay. So another notation, another way of representing vectors. We talked about the x component, the y component, and the z component as simply just those three numbers. Well, there's a notation that actually emphasizes that very strongly. So the idea is to say, to talk about x direction units, y direction units, and z direction units. So the way that we do that is that we say that the x direction is represented by the vector I. So I is 1, 0, 0, which is the unit vector in the x direction. J is the unit vector in the y direction, and k is the unit vector in the z direction. Now a quick comment, I is the unit vector in the x direction, that's always true. Now if you're in 2 dimensions, that would just be 1, 0. But in 3 dimensions, you need to write 1, 0, 0. But either way, it's still the unit vector in the x direction. Okay. So what does this mean that we can do for vectors? So the old notation was to write it as x comma y, or in this case, u1 comma u2. The other way to write this is to say we're going u1 units in the x direction, and then also u2 units in the y direction. And here's the way that you use this ijk notation to write that down. You say u1, which is a number, multiplied by the I vector, plus u2 multiplied by the j vector.
So you could say that I vector is an identity vector for x, right?
Okay. So that's in 2 dimensions. And then in 3 dimensions, it would look like this. So if you have the vector v1, v2, v3, then that would just be v1 times the vector I plus v2 times the vector j plus v3 times the vector k. That just means v1 units in the x direction, v2 units in the y direction, v3 units in the z direction. Okay. So notice that in this sense, v1, v2, v3 are telling you magnitudes, and I, j, k are telling you directions. Now what's the magnitude of I or j or k? Their magnitude is just 1. So in a sense, we've removed magnitude information from I, j, k. So that's why we call them units. Well, that's the reason they're called the unit vector. So they, in a sense, they only tell you the direction, and then you need the v1 or v2 or v3 to tell you what the magnitude is. Okay. So I, j, k, just terminology, are called the standard basis vectors. So here's a vector. Let's rewrite this using the standard basis vectors. So 3 comma negative 4 comma 1, what is that in standard basis vectors?
3i minus 4j plus
There you go. It's 3i minus 4j plus 1k, or just plus k. All right. So again, this notation just puts a strong emphasis on the components themselves. The x component, the y component, the z component. Okay. 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 2 comments. One, the first comment we've sort of hinted at, and now I'm going to say it directly. There is no distinction between the notation for a point and for a vector. There's a reason for that. You could think of a vector as a point, or you could think of a point as a vector. If you give a point, it's a vector because we could think of the starting point as the origin, as we said before. And likewise, if you have a vector, you can just think of it as those are the coordinates of a point. So now this equivalence between vectors and points can be very useful. It can also be confusing. So the best I can say right now is keep this in mind as we go forward and cover more topics. Okay. But we're so used to using points, I wanted to address this specifically. Okay. And another reminder, so far everything we've talked about, we've done in both 2 dimensions and we've done it in 3 dimensions. And it also applies in higher dimensions as well. On paper, as I said, on paper, it's always easier to draw things in 2 dimensions, the 2-dimensional picture, as opposed to trying to draw the 3-dimensional picture, which gets, the perspective is very difficult. So therefore, most examples, I'm going to draw in 2 dimensions. And a lot of the explanations will be in 2 dimensions. But it also works for 3 dimensions, just harder to visualize or draw. Okay. One more thing, the length of a vector. To find the length of a vector, you're going to use the distance formula. Exactly. So the length, also called the magnitude, also called the norm, and you can calculate it by using the distance formula, and you just take the origin as the starting point. Okay. So there's the notation. We write bars around the vector, and that means the magnitude. Some people use single bars, some people use double bars, either one. It's just this. Now this is simplified, so I said use the origin as the starting point, but what happens when you use the origin? You just get v1 minus 0. So the minus 0 part just goes away. So let's calculate this. So what is the magnitude of this vector? It's five. Oh, come on. Okay. 5 squared plus -2 squared plus 4 squared, and then square root of the whole thing. That's the square root of 25 plus 4 plus 16. That's just the square root of 45. And that's approximately like 6.9, something like that. It's close to, so that's close to 49, so this is close to 7. I don't know, it's about 6.9, something like that. Okay.